get this show on the road. Hello, everyone. Hope you're well. Welcome to or no. Now I can see myself. I don't know if you guys are seeing me, but it seems like everything's fine now. All right, let's jump into it. We were talking about stuff about derivatives and finding them by definitions last time. So let's actually jump back into that and learn some more about derivatives. So let's make sure I can see the chat here. Just as a quick recap, last time I remind you guys that we figured out something called the derivative was a solution to the rate problem, helps us to find the slope of a tangent line to a curve at a certain point, which in turn could help us figure out the average rate of the instantaneous rate of change at some point on the function, which is we could actually use it to figure out how fast is the output variable changing in relation to the input variable. Very interesting stuff, very sophisticated solution to the rate problem. We spoke about the two different notations, the Newton notation and the Leibniz notation. I'll mostly be using the Newton's notation in this class, which is the prime notation. You put that little notch, almost like an apostrophe. It's not really an apostrophe though, if you actually look at the symbol, whatever. How we can interpret the derivative, right? So f prime is the derivative of f. Derivative is a synonym of slope. It's synonymous, means exactly the same thing. Derivative is just a little bit more general. Slope is what we use when we were talking about a straight line, right? Pretty much the instantaneous rate of change at any point and average rate of change really for a straight line. We say derivative when we want to talk about that concept for anything in theory, right? It also gives you the slope of the tangent line at a point, the instantaneous rate of change at a point, how fast the y value is changing in relation to the x value, or more generally, how fast the output is changing in relation to the input. And it gives you a formula for figuring out all of the above. So here we did a very typical example where I asked you to use the definition to find the derivative of some function and to use that information to find the equation of a tangent line. And we went through that, a very important example, definitely something that's coming up. And then we just found a bunch of other examples. We also found some rules where we can use these as shortcuts, which we will actually revisit that idea in the future. So eventually when we're in the next chapter, next section, I don't remember, but soon we're actually going to talk about a lot of shortcuts, how we can find derivatives a lot quicker than actually going through the limits. But for now, so for this class and actually next class too, the next like two-ish classes, it's going to be mostly information dump. Like I'm going to tell you a lot about the derivative. We're not really going to be focusing on examples per se, but just some interpretations and ideas and concepts that are important regarding the derivative, so that when we get to situations like word problems and other things I'm going to ask you, you know how to kind of navigate them, right? So one thing we saw is the derivative's role in actually identifying when a function is increasing versus decreasing. So it turns out using the sign of the derivative, knowing whether it's positive, negative, or zero, can actually tell us how a function is behaving in terms of whether it's increasing or decreasing, right? So if our derivative has a positive sign, it means that in that region, your function is moving up as it goes from left to right. If we have a negative sign, it means that in that region, your function is going down as it moves from left to right. So you can actually talk about the derivative and what it can tell you about increasing and decreasing. So that was cool. And basically, if I have some interval, and then if we know that the derivative is positive on that interval, it means whatever the function is doing on that interval, it's always moving up as it goes from left to right. And if your derivative is negative, then it's always moving down as you go from left to right. We call these increasing and decreasing. Okay. And so today I'm actually going to tell you more stuff like this, right? Like what kind of interpretations we can put on the derivative and just some general frameworks in which we can make these interpretations. So that's the focus of the next couple of classes. And the discussion starts with the concept of higher derivatives. So let's actually talk about that. Higher derivatives. it turns out sometimes we can take derivatives repeatedly. In this class, that's pretty much always going to be the case. We're dealing with very nice functions that are what we call infinitely differentiable, which means you can take a function, you can find its derivative, and then you can find the derivative of the derivative, and then the derivative of the derivative, and you can keep like going on forever. Not all functions do this, but you usually aren't introduced to functions that don't have that property in Calc 1. So yeah, to you, it might seem like a moot point because everything that we cover in this class, you're going to be, yeah, that's obvious, but it's not true in general that you can always just differentiate whenever you want. But there are times when we have functions that we can just keep differentiating them, just keep differentiating, keep differentiating, keep differentiating. This leads to what we call higher derivatives. So that, i.e. find derivative of derivative of derivative of derivative of derivative. Okay, so let's talk about some notation for this. So let's talk about the Newton's notation. The Leibniz notation. And the derivative we're talking about. So, assume y equals f of x is a differentiable function, repeatedly differentiable. Okay, so how do we denote this? Well, let's talk about the notation. So first, let's talk about just the function, which we might call y. And this is called, actually, the original function. This is the original function. It's called the zeroth derivative. Right, so that's just the original function, no big deal, right? So our original function, we think of it as the zeroth derivative. This is the function I've taken no derivatives at this point. Now the first derivative is what we saw, that's the prime notation. We saw this last time, so this is the first derivative. Now, what if we took the derivative of the derivative? What would that look like? Well, turns out in the prime notation, you just add the notches, right? So I put 2 primes for the second derivative. For this guy, we put d squared y dx squared. And the reason is, it's because we took the derivative of the derivative. So the dx portion gets squared and the d in the top gets squared. And so you get that. This is called the second derivative. Right? Sometimes you can keep going. You have f triple prime. This is d cubed y dx cubed. This is the third derivative. Now, obviously, if this keeps going, the prime notation is going to get highly annoying. So let's say you're way down at like the 17th derivative, right? You don't want to have like 17 notches in the thing. That's going to be weird. So what you do is you actually write it as a power, but you write it in parentheses. So you can say something like f in parentheses up top, I can say 17 of x, right? Or d17y dx17. This is the 17th derivative. Okay, so in general, what you see is that ultimately the notation becomes f to the n in parentheses of x dn y dxn. It's called the nth derivative. In fact, the original function, in some context in calculus 3, you don't have to worry about this really, you would write this as f to the power 0, but you put the 0 in parentheses, so you know it's not actually the power 0, which would just always make it 1. It's actually the 0th derivative, right? So that's the notation for the higher derivatives. Now, it turns out that these higher derivatives can have very convenient interpretations. Higher derivatives may have convenient interpretations. We are mostly going to be interested in the second derivative as our main applicable higher derivative. Not because it's the only important one, but for the applications that we're going to do in Calc 1, the second derivative is going to be the most we need in general. I don't think I ever asked anyone to compute like a third derivative or fourth derivative, but if I ever ask that, it will just be a computational problem and you won't really have to do anything with that information. I'll just ask you to find it just to see if you knew what it is and how to find it. But in terms of what we can actually use, the second derivative is going to be higher, is going to be the highest one we're going for. So for us, the second derivative will be important. So I want to spend some time talking about the second derivative. This is the derivative of the derivative. So you find the derivative, you get a function. What if you were to find the derivative of that function, right? That function that you just got, right? So this is the derivative of the derivative. Okay, turns out that can tell you a lot of applications. So many applications. Here are two that are important to us. So one application is to the physics of motion. So basically, and traditionally, we use S here. So here, let's say T is just time. Then S of T, this is the position function. Right? So where are you at time T? What is your position, right? That's the position function. So it turns out if you were to take the first derivative of the position function, this we call v of t, and it is the velocity function. Velocity is speed, but it's speed in such a way that you can tell what direction you're moving in. So with velocity, for us, there's usually going to be only two directions. So a positive velocity value might mean moving to the right or upwards, while a negative velocity value would be moving to the left or downwards. So this is a speed in a certain direction, speed in a particular direction. To talk about other directions than left or right or up and down, you would need like vectors for that, and really you only get into that into like Calc 3, so you won't really have to worry about that. But that's the velocity function, so that's the interpretation of the first derivative. However, we could actually, in general, take another derivative. You could actually take the second derivative up the position, right? And this is the same as the first derivative of velocity, and we call that a of t. It's actually the acceleration function. And this is the rate of change of velocity, rate of change of velocity. This guy, by the way, is the rate of change of position. Right? So these derivatives, using derivatives, we can answer different questions. So if someone says, where are you? Use the position function. If someone says, how fast are you moving? Use the velocity function. If someone says, are you speeding up or slowing down? Use the acceleration function. They answer very different questions. So this is the answer to, where are you? Where are you now, right? Position function. How fast are you moving? That is the first derivative. That's the whole point of the first derivative, right? To solve the rate problem. The second derivative actually answers a different question. Are you speeding up? And that's what acceleration tells you about. It talks about the rate of change of speed. Yeah, I know how fast you're going, but are you currently getting faster, or are you currently getting slower, right? That's a different kind of question, right? And by the way, constant to know. There is the acceleration due to gravity. Anyone knows what that is? Did you come across this in your other classes, maybe a very basic physics class?
I remember it in physics a while ago.
Yeah, well, what, you remember the number? So there are two measurements depending on whether you want to go metric or not. Right?
Isn't it 9.8?
9.8. So it's minus 9.81. The minus indicates that it will pull you down towards the Earth. And this is in meters per second squared. Or minus 32 feet per second squared if you're American. So those two numbers you should know, right? So the acceleration due to gravity is 9.81 meters per second squared, or 32 feet per second squared. So if you're above the Earth at some point and you drop something, after 1 second, it will be traveling at 32 feet per second. After another second, it will be traveling at 64 feet per second. Eventually, it's going to hit something called terminal velocity where it doesn't actually speed up anymore. But until that point, every second that passes, it will add 32 feet rate of change to its current position. And yeah, so that's what the acceleration would actually tell you about, right? So the Earth, on average, it depends on where you are technically, but these numbers are the average values. Earth will pull you down towards itself and speed you up at these rates. So if your speed was 0 1 second ago, now it's 9.8 meters per second. Okay, so yeah, so that's an important application. There is something called, there is a very nice physics interpretation of the third derivative as well, by the way, which is So that's position, velocity, acceleration. Turns out the third derivative is actually called a jerk. That's like the technical definition. So, you know, if one of your friends call you a third derivative, it's not a compliment. Just I saw t-shirts like that before, like, yeah, people not knowing what it means, and I'm like, it's calling you a jerk. Okay, so another very important application. There's something called concavity. Okay, so for us, there are two kinds. There's what we call concave up and concave down. Okay, now I'm going to explain what these guys are, how you can identify them using derivatives, etc. So talk about concave up. Definition. F of x is concave up on an interval I if its graph always lies above its tangent lines. On I. So what does that mean? Here is my function f of x. If at any point I were to sketch a tangent line, notice that the function is always going to be above the tangent line, right? These are tangent lines. Notice that they're always below. Right? So a function that exhibits this property, we say that the function is concave up wherever it exhibits this property. Now, here's what I want you to notice about what's going on here. What is happening to the slope of the tangent lines as you move across this thing? All right, so one tangent line might be over here. It's like this. Describe to me what's happening to the slope of the tangent lines. Until you get here, and it's like that.
They're getting steeper, so they're increasing.
They're getting steeper. They're increasing. So the tangent lines are getting steeper. This means their slopes are getting bigger in the positive direction, right? So in other words, if I were to track a function to track the slopes, that function would be increasing. But we do know a function that tracks the slopes. That's the derivative, right? So slopes are increasing. But remember, slope is just a synonym for derivative. This means derivatives is an increasing function. Now, last time we learned what it meant to be increasing. F was increasing if its derivative was positive. So me saying the derivative is increasing is the same as me saying the derivative of the derivative is positive, right? So this means f prime is increasing. And that means the derivative of f prime, which is the second derivative, is positive. by what we learned last class. I.e., f is concave up on I if the second derivative is positive on I. So it turns out whenever a function has this behavior, I can identify when it would have that behavior by simply looking at the second derivative. I can say, this is the second derivative positive? Then I know it has this behavior. Okay? So almost similarly, what if the opposite were to happen? Did I give that a whole other section? Yeah, similarly, let's talk about concave down. F is concave down on I if it always lies below its tangent lines. So here's an example of a function. Let's call it f. Let's say every time I draw a tangent line, the tangent line is sitting on top of the function, right? Function that exhibits that quality is said to be concave up. And I want you to notice slopes are decreasing, right? They were very positive, but then they're becoming zero in this particular example, right? They're getting smaller. Slopes are decreasing. This means f prime is decreasing. And that means f prime prime, which is the same as f double prime, is actually less than 0. So then we get f is concave down on I if f double prime is negative. So when the first derivative is positive, that means the function is increasing. If the first derivative is negative, it means the function is decreasing. If the second derivative is positive, it means the function is concave up. If the second derivative is negative, it means the function is concave down. Concave up and concave down means that they exhibit this behavior. But let's actually talk a little bit more about concave down so intuitively really understand what we're talking about, because it's about shape, right? So that's what I want you to notice. So because I say positive and negative, you might be tempted to think that, oh, it's moving up or it's moving down. No, it's not about moving up or moving down. It's not about even the outputs of the function being negative or positive. It has nothing to do with that. Concavity is about shape. It has nothing to do with a function increasing or decreasing or being positive or negative. Examining the sign of the second derivative tells you about the shape of your function. It doesn't tell you about what values it's taking on. It doesn't tell you about whether it's moving up or down. And to illustrate that, I want you to just note, you can be concave up whether you're increasing or decreasing. So I can be concave up doing that. That's concave up. Tangent lines will always be below the function. But I could also be concave up here just by doing that. Tangent lines would also be below the function. So here, notice that this is concave up and increasing. While here we're concave up and decreasing, right? So you can be concave up in either scenario. You don't So concavity has nothing to do with whether you're increasing and decreasing. It's very important that you understand that. It's about the shape while you're increasing and decreasing. So the mnemonic to remember, mnemonic starts with M, I think. You say concave up like a cup. Concave up like a cup. It's shaped like this. You can hold something in it. It's like a smiley face. You're concave up, your second derivative is positive. You're positive, you're feeling happy, you smile. The concave up like a cup. That's what it's about. It's about the shape, right? It's not about whether you're actually moving up or down. It's about how you're shaped while you're moving up or down. If you're shaped like a smiley face, you're concave up, right? Versus, you know, concave down. Again, you can be increasing in concave down, or you can be decreasing in concave down. So this is concave down and increasing. This is concave down and decreasing. Right? So you can be either. This also has a mnemonic. Concave down like a frown. Right? So you're down, you're feeling negative, second derivative is negative, you frown, upside down smiley face. That's what concave down means, right? So you're either shaped up like a cup or down like a frown, right? And you can identify these by the second derivative. Okay. So that's one thing I want to make sure that you get. Concavity is about shape. It's not about increasing or decreasing or being positive or negative. It has nothing to do with any of that. It's about shape. Do you shape like a cup or do you shape like a frown, right? So that's an important idea. Now, another important idea is the idea of an inflection point. So a point of inflection of a function f of x is a point on its graph where it switches concavity. Okay, so if you can identify a point on your function where it was concave up before, but then it went through this point and now it's concave down, or vice versa, was concave down before, went past through this point, now it's concave up, you say you've gone through an inflection, right? So that you can have various scenarios. So you can have something like that, or you can have something like that. You can have something like, let me do two increasing ones and two decreasing ones right away. Or you can have something like that, decreasing, something like that. Or you can have something like that. And these points right here are points of inflection. You can notice what was happening if you were to, on this side, you are concave down. How do I know? Because it's shaped like a frowny face, down like a frown, right? While on once it passes through the blue point, from that point onwards, it's concave up like a cup, it's smiling. So at that blue point is where it switches from being concave down to concave up. Now it's continually increasing the whole time, but it changes how it's increasing. It changes its shape while it's increasing, right? So whenever you do that, you say you've passed through a point of inflection. That's what that's called, right? And it's when you change concavity, right? Now, I want you to consider what this means, especially if interpretation meaning is given to our variables. Okay, so mathematics is an abstract study, and it's lost on a lot of people why it's worth it at the end of the day. It's like, okay, I went to calculus class and I learned about graphs and about smiley faces and frowny faces. Whoop-de-doo. What's the big deal? The big deal is what it all means. Now, it's very rare that in real life you're going to care specifically about the specific function, right? Like the fact that, oh, it's a picture. Okay, why do I care, right? It's not about the picture or about the function. That's not where the math helps you. It's just that by knowing the math, it can actually tell you something about the function. And you start to care when the function itself takes on meaning for you, when your x value has meaning to it and your y value has meaning to it. So these four pictures that I have here, if you start to give interpretation, they can have very different meanings and they can be good or bad depending on what you're talking about. So for example, let's say these are graphs of a function that's tracking my profit over time, right? Some of these are good and some of these are bad. And some of these are better and some of these are worse. Now, if this function represented, say, the profit I make from being a business owner, then what would I want to happen? Well, this is the best scenario over here for sure. Now, I mean, either of these is good, but this one is better, right? So, and why is that? I want you to understand what the inflection actually means. Increasing or decreasing is telling you about whether it's moving up or down from left or right. What concavity tells you is whether or not it's speeding up or slowing down, right? So here, whenever something is concave down and increasing, I didn't mean to restart. Whenever something is concave down and increasing, it means that it's increasing, but it's increasing slower and slower, right? So it's getting bigger, but the amounts by which it's getting bigger, those amounts are getting smaller, right? So it's increasing, but it's increasing slower and slower over time. Or it's increasing, but it's increasing faster and faster over time. That means you're concave up while you're increasing, right? And so there are a lot of nuances to science that this is really where it comes from. It's from people understanding the math enough to be able to do that. So for example, controversial issue, you can talk about global warming and people say, well, the earth has always been heating up. I mean, this is not a big deal. But they're like, no, you see, the way it's heating up is the big deal. It's heating up faster and faster. The graph is concave up in an unprecedented way, right? So it's not just that it's moving up from left to right. We're not just on the first derivative level of thinking here. We're moving on to the next level of thinking, the second derivative level of thinking, where it's like, it's not just about the up or down. It's how it's moving up or down. It's moving up faster. And that is a problem, right? So you can actually interpret the data better once you start to understand the math and what it means, right? By examining the second derivative, you can not only tell if something is, you can tell how fast something is moving up or down in the sense that, is it increasingly moving up or down? So what you'll understand in the leftmost graph here, what that means is it's good. My profits are increasing, but they're increasing slower and slower. Maybe, my popularity of my business is going down. People they've seen it, they've been there, they've done that. But then something happens. Suddenly, now more people are interested in my product. What happened at that point? Did we try a new marketing strategy? Did we offer a new product? So if I'm looking at my graph, I would want to know what happened at that blue point. I'd want to identify the blue point, and I'd want to know what happened during the time period that blue point occurred, because it's going to tell me something changed at this point. Kind of like the blue dot would be on the time scale of the Earth, would be at the Industrial Revolution. We're like, yeah, we kind of know it's because of this, because that's where the blue dot is on this picture, right? So you can say, well, it's not just normal every day. It's like billions of years it was like this. The blue dot happened, and now it's like this. I think something is going on, right? Here, the second graph is a little bit, it's still good news, but it's less good news. So at first, my product was super popular and it was selling like crazy, like hotcakes. People couldn't get enough. Week after week, I had more and more customers. Yeah, we're still in the green. I'm still making profits, but after that blue dot, I'm making less and less profit over time, right? So maybe the customers are getting tired of stuff and I need to like do something, right? Versus here, it's like, well, this is bad news. We are bleeding profits. However, there is hope. We were way worse before, but now we're getting a little better. We're not losing as much money as we were losing before, right? Whereas here, dude, it's bad and it's getting worse. Like we were losing money before, but now we're really losing money. Like you understand, like there's an interpretation. Like once you put an interpretation on the graph, you can understand why is it important to know about concavity? Why is it important to know about inflections? This is why the interpretation matters. If I gave you a completely different interpretation, then everything changes. If I were to say, these graphs are measuring the size of a malignant tumor in your lung, well, this one is the best, right? You want that size to be decreasing, and the faster it decreases, the better, right? Whatever meds you put me on at that blue dot, that's doing something that wasn't happening before. Versus, if I'm all the way to the left, that's bad. It's growing and it's growing faster, right? The second graph, it's bad, but it could be worse. It's growing, but it's growing slower. So something we're doing is slowing it down, right? So there's a whole kind of interpretation that can go along with this. So it's not about, oh, here's a picture and shapes like a frown or this and the second derivative, rah, 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 rah. No, it actually can mean something. And if you understand that, it makes you better at interpreting data and not missing when something important happens. So just want to make sure you know about that. So knowing when something is increasing or decreasing is important. Knowing where inflections are and concavity is important. So knowing that they're important and knowing how to identify them with derivatives, how do we have a mental framework of how to approach something and actually figure these things out, right? Give me a random function. How do I actually go in and figure out where it's increasing, where it's decreasing? How do I go in and figure out where it's concave up, where it's concave down? Is there a point of inflection, or et cetera, right? It turns out that there are tests. There are tests that can tell us about when, where behaviors like above and last class occur. So there are two important tests for us. One is called the first derivative test. This is the framework in which you go in and your goal is to figure out, is it increasing or decreasing? And bonus points, we can actually figure out where maximums and minimums occur. So this is to figure out increasing, decreasing, as well as maximums and minimums. So where would the maximum profit be? Where would the minimum profit be, right? You can use a test called the first derivative test to figure all that out. The other test is called the concavity test. Now, it will be obvious to most people why you would want to know if something is increasing or decreasing or max or min, but people are just seem less concerned with finding out about concavity, but it's actually really important. Hopefully my little rant earlier convinced you of this. But this is a test to figure out concavity and inflections. Because wise people know it's not just about increasing or decreasing. How you increasing or decrease matters as well, right? It's not just all about the maximum and the minimum. It's, are you an inflection or not? Is also important a lot of the time. So, I mean, there's a third test that we don't really care about. 3, common, important test. Jhevon doesn't care about. Is called the second derivative test. And really, it finds max and mins, right? So 1, the first derivative test gets you that and more. So that there's that, right? So it's kind of like, if I'm doing the first derivative test, why would I even need the second derivative test? I already got the information the second derivative test would give me, and I got more. So I don't really know why we're doing this. So that's one thing. And it's just like, and the second thing is that for what I will be asking you guys to do in class, you will be doing the first derivative test and the concavity test anyway. So then doing the second derivative test is just extra. It's superfluous. It's not necessary. So it's going to be kind of useless for us. However, it can be important in some contexts if you already have certain information and you just want a little bit more information, sure. But in a Calc 1 class, I really don't think it's that important, because I'm pretty much going to be asking you to do these 2 tests all the time. And once you do the first test, this one becomes useless. Like, you don't need it. Like, you already have all the information it could give you. But yeah, so we'll talk about that next time. So we will wrap up there. So next time, I still have a lot of information to give you. Hopefully we can get to something where we do a bunch of calculations, but I don't know, maybe that might spill into Tuesday before we can get that. But just understanding the concepts of why the derivative is important, what it can tell us. It turns out it's not just about answering the rate problem. We answered the rate problem, but we actually got a lot more at the same time. We got a lot of extra with this ability, right? Turns out figuring out how fast something is moving helps you figure out a lot of other things as well. And we'll get into those things next time. So for now, we will end right there. So hopefully that was clear, just a bunch of stuff to know. I'll leave up the notes and you guys review it for next time. Until then, I'll let you guys go. See you in the next one.